of corresponding sides in its lowest integral form is called the scale factor. So just kind of reviewing what's written on the sheet here. And all corresponding length measurements have a ratio equal to scale factor. Some of those length measurements can be sides, diagonals, heights, perimeters, whatever. So that's just kind of review what's going on. But just as a quick picture of that, maybe, let's go ahead and draw very quickly a triangle. And then I'm going to make a similar triangle to that. Whoops. Okay. So these two triangles are similar, which means if this is, say, 3, 4, and 5, and this would be 9, 12, and 15. So if I take the ratio of any two sides, corresponding sides, say 5 to 15, that reduces to 1 to 3, which is my scale factor. And we often express it that way. And so any length measurements, we're at the ratio 1 to 3. 4 to 12 is an example, or 3 to 9. Also, if you look at the perimeters here, the perimeters would have the same thing. 3 plus 4 plus 5 is 12. So this perimeter, if we predict, if this ratio is 1 to 3, if there are 3 units of length for every 1 unit of length here, that would be a perimeter of 36. And when I check that, 9 plus 12 plus 15 does indeed equal 36. So the perimeters, all the length measurements in similar figures exist at the same ratio, which we call the scale factor. And that's what we did. Again, here I have two triangles, 4 centimeters and 10 centimeters of corresponding sides. What would the scale factor be? Well, we'd take the 4 to 10 and reduce that to 2 to 5 would be my scale factor. Therefore, the ratio of the perimeters would have to be the same as the scale factors because perimeter is a length. So we'd still be 2 to 5. Area is not a length measurement. This should not be a shock to anybody. But nonetheless, let's highlight it. Therefore, the scale factor does not equal the ratio of the areas. For example, here I have two squares. The scale factor is clearly 7 to 10. That's the scale factor. The areas of the two circles are 49 centimeters squared, or circle squares, and 100 centimeters squared. So if I take the ratio of the areas, that's 49 over 100. Or, if I want it the other way, 49 to 100. That would be the ratio of the areas. Does that reduce to 7 to 10? No. Square root is not a way to reduce. Reducing is by division. In fact, that doesn't reduce at all. So what do we notice about the relationship between the scale factor, which, by the way, would be the same as the ratio of the perimeters, and the ratio of the areas? What's going on there? Well, I think it's pretty clear from these numbers that the ratio of the areas is the square of the scale factor. The ratio of the areas is the square of the scale factor. So, going back here, actually, we'll just add a page in. If I have a scale factor of A to B, that applies to lengths. So the ratio of areas is going to be A squared to B squared. And that, of course, applies to areas. It's supposed to be an E. Okay? So a pretty simple concept. So let's take a look at this. I have two similar octagons that have areas of 50 centimeters and 32 centimeters squared. The side of one larger octagon is 7.5 centimeters. Find the corresponding side in the second. Now, a picture certainly may help. I do have the advantage of being able to draw octagons with the smartboard, but that's okay. The ratios are 50 centimeters squared and 32 centimeters squared. So the ratio of areas is 50 to 32, but I can reduce that because both are even numbers. So 25 to 16 would be my ratio of areas. If my ratio of areas is 25 to 16, my scale factor, which I use for lengths, is going to be the square root of that, or 5 to 4. One of the sides in the larger octagon is 7.5. What is the corresponding side here? That's what the question's asking. So now we solve that with proportions. Since I know the scale factor is 5 to 4, that's going to be 7.5 to x. I can cross multiply that. 4 times 7.5 is 30. It's 5x, so divide by 5. And I get that this side is 6 centimeters. So how did we attack this again? We took the ratio of areas, we reduced it. And we took the square root of the ratio of areas to find the scale factor because we want to compare lengths. Lengths need to be compared using the scale factor, not the ratio of areas. Very common mistake people will make is they will use the ratio of areas to try to compare lengths. You cannot compare areas with lengths in the same proportion. It's all areas or it's all lengths. That's the way it goes. If you double the lengths of the sides of a square, how do you change the ratio of the areas? This is a very common problem in a lot of things. People say, I want to double the size of my square. So they double the lengths of the sides. So this is x, and this is 2x. But did I really double my square? No, I didn't double it. And now my measurements probably here aren't exactly, so I'm going to see if I can get this close to double. Okay, let's make this a little bit bigger. 1, 2. Okay, so how many squares do we have here? There we go. How much should I increase the area? 1, 2, 3, 4. Why? You can see that again. The scale factor would be x to 2x or 1 to 2. So the ratio of areas is 1 to 4. And we can clearly see that taking place. Even though the side is only twice as long, the area is 4 times as much. Volume just adds one more level to this. If the ratio of, if there shouldn't be a ratio of areas here, that is a typo. If the ratio of the lengths is a to b, then the ratio of areas is a squared to b squared. What would the ratio of the volumes be, do you think? And that's the question I want you to answer. It's a very simple question. If the ratio of lengths is a to b, and the ratio of areas is a squared to b squared, therefore the ratio of the volumes would be what? And you should be able to figure that out pretty simply, or you can look it up in your lesson, and that's in chapter 12. So that's our final podcast of new material for the entire year. And I hope you've enjoyed the flipped concept. We'll be reviewing shortly and taking our final quiz and then our final exam. Our final test and our final exam. So I'll talk to you again soon. Thanks for listening to the podcast.